In this video, we will talk about finding a formula for the number of combinations in general. So I want to begin with that goal. We're trying to find a formula for the number of combinations of k objects from a set of n objects where the order does not matter. So I want to begin by labeling our set of n objects. And I'm going to put this in set notation, so let's put some curly brackets. And let's label the elements in it as x1, and then x2, comma, and then I'll keep going like that, dot, 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 comma, until I get to the last element, which I'll call x sub n. So there's n of these elements. That's why it goes from x1 up until xn. So let's recall that we know how to find the number of ways to just permute k objects from a set of n objects. And when we permute these k objects, that means we're talking about a situation where the order in which we pick those objects matters. And the way we set that up was, we thought about, okay, how many choices are there for the first object that we end up choosing? Well, there's n objects, so there's n ways to pick which one goes in that first slot. And then I think about, well, how many ways are there to choose that second object? Well, once we've picked the first one, there's still n minus 1 to choose from, and that's how many go in the second spot. Notice I'm going through this a little bit more quickly than we did before, because we've seen this formula a few times now. Okay, and then for the third object picked, now we've already picked 2 to occupy the first 2 slots. So there's n minus 2 choices left for that third object, and we keep going like this times, oops, let me put a dot, 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 until I get to the last slot. Okay, and for the last slot, this is still going to be n minus something. But recall that this is the kth object that we're picking here. And there have been k minus 1 objects already picked at this point. K minus 1 objects already picked. And that's why we're still going to have n minus k minus 1 choices left for this last object, for this kth object. And if you distribute the negative sign, we get n minus k plus 1. And that was the number of ways to permute k objects from a set of n. So recall our notation for this number of ways was p of n comma k. So we have p of n comma k is n times n minus 1 times n minus 2 dot, 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 times n minus k plus 1. This formula counts something like x1, picking x1 first, and then x2, and then x3, and then picking xk as being different from having those same objects, but in a new order. Like, what if I reverse the order? So I did xk first, and then xk minus 1, comma, dot, 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 until I get to x2, and then x1. Because when I count the number of permutations, that's saying the order matters. So if I switch the order of my objects, this formula is counting those as different things. Okay, but in my goal right here, when we're counting the number of combinations, we want the order to not matter. Okay, so I'm going to add the words when. We now want them, and by them I mean these two selections, x1, x2 up until xk, and then the other selection xk minus 1 up until x1. We want things like this to be considered the same because the order is not supposed to matter in a combination. So for our purposes, this is the same collection of k objects. So what we're going to do, as we saw in the last video, is we're going to think about how many ways can these k objects be permuted. These can be permuted or rearranged in, so there's k objects that we've chosen, k objects in this list, so they can be permuted in k factorial ways. And as we saw in the last video, the way we're going to fix our initial count, this formula that we had for the number of permutations, to get the number of combinations where the order doesn't matter, is we are going to need to divide by k factorial to fix the overcounting. Essentially, every collection of k objects is getting counted k factorial times under this initial formula that we have. All right, so we are now ready to write down the number of ways. Oops, let's put this in gray actually. The number of ways to select k objects from a set of n objects where the order does, and let me put this in red, does not matter. And the formula for it is we take what we had before, n times n minus 1 times n minus 2, dot, 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 until I get to n minus k plus 1. And then we divide it by k factorial, because we ended up overcounting by a factor of k factorial. Okay, so this is going to be a formula for counting the number of combinations, and I'm going to highlight this. This is an important formula for this section. So next, let's look at an example. All right, so this example says that a lottery requires choosing 6 distinct integers among 1 through 55. How many different lottery tickets are there? Okay, so the first thing that I want to mention is when it says the word distinct, this just means that they're different. So so these are different. They're different numbers. We have to pick 6 different numbers. And the other important thing about this question is that the order does not matter. We just care about what 6 numbers are on the lottery ticket. We don't care what order that they're in. So because of that, we are going to use combinations. And I know that at some point, because the order doesn't matter, we are going to have to fix our overcounting. So let's practice using our notation for combinations. I'm going to use C, and then we're choosing from a group of 55 numbers. We're going to choose 6 of them, 6 different numbers. So the way we do this is we think about, okay, for the first number, we have 55 choices. For the second number, we can pick anything except for what we picked first, because they got to be distinct, different numbers. So 54 choices left. Then for the third number, we could pick anything except for what we picked for the first 2 numbers. So that gives us 53 choices. And we just keep going like this, and we have to, in total, pick 6 numbers. So I should be multiplying 6 numbers. So 55 times 54 times 53. Then I do times 52 times 51 times 50. All right. And now I got to adjust for overcounting, and I got to think about, well, how many ways are there to permute these 6 chosen integers? Because I don't care about their order. So there's 6 factorial ways to permute them. So this adjusts for overcounting. For the overcounting. And I can verify that this fraction that I'm coming up with matches up with the formula that we had. Specifically, I could look at the last number in my list, and this should give me the n minus k plus 1. That's what our formula for combinations says this last term should be. Because if I plug in n is how many elements are our original set, which is 55, minus k is how many elements we picked when we picked 6, and then plus 1, and if we work this out, this is 50. So it's matching up with what we got there for that last value. And if we plug this into a calculator, we get a huge number. We get 28,989,675. So we have that many different lottery tickets. All right, and just to practice using our other notation and how we'd say this in words, this C of 55, 6. In words, we say this as 55, choose 6. So one thing that I sometimes say in my head to tell myself it's a combination and not a permutation is, if all I'm doing is just choosing some number of objects from a big list of objects, and the order doesn't matter, then that tells me I think of the word choose. And when I see the word choose and order doesn't matter, I think of combinations. Okay, so another way to say this is we are choosing 6 elements from a set of 55 elements. All right, so I want to note something about this. I want to note something about how I initially wrote my answer, because there's another way I could express it purely in terms of factorials. So 55 times 54 times 53 times 52 times 51 times 50, whoops, all over 6 factorial. I'm going to multiply the top and the bottom by something. I can complete the factorial on the top if I multiply the top by 49 times 48 times 47 times ... until I get down to 1. I'll multiply by the same thing on the bottom. 49 times 48 times 47 times ... times until I get to 1. And if we do this, now the top, the numerator, is 55 factorial perfectly. And on the bottom, well, we have that first 6 factorial. And then this other stuff that we put on the bottom is 49 factorial. Okay, so that's going to lead me to another way that we could write these number of combinations in general. So in general, we can write C of n comma k. This is the notation for the number of combinations of k elements from a set of n elements. Remember, order doesn't matter in combinations. So our formula initially was n times n minus 1 times n minus 2, until n minus k plus 1. And then we divide to adjust for overcounting in combinations. We divide by k factorial. That's the number of ways to permute those k objects that are selected. Okay, so this was, I'm going to call this formula 1. We're now going to get another formula. So I'm going to write down the same thing that we just had. n times n minus 1 times n minus 2, up until n minus k plus 1 over k factorial. And just like we did in the example above, I'm going to multiply the top and the bottom by something to complete the factorial on the top. So if I subtract 1 from this last term, n minus k plus 1, I get n minus k. And if I subtract 1 again, we get n minus k minus 1. And if we keep doing that, eventually we're going to get down to 2 and then down to 1. Let's multiply by the same thing on the bottom. N minus k times n minus k minus 1, times 2 times 1. Let's close that parentheses. And now on the numerator, I have a perfect factorial. We have n factorial. And on the denominator, we have k factorial. And then the other stuff in blue on the denominator becomes n minus k factorial. So I'm going to put this whole thing in a box because its box is going to summarize two of the formulas that we have to count the number of combinations. So this over here, I'm going to call formula 2. And both of these are important, so I'm going to highlight both of them. The first one we had already seen, the one I'm highlighting right now. And here's the second one, purely in terms of factorials. So let's do one example to end this video, practicing this notation. So let's compute C of 12, 8. So we're counting the number of ways to select 8 objects from a group of 12 objects where the order does not matter. Okay, so C of 12, 8. I want to do this just practicing my factorial formula. So let's see. That means this is n, and this is k. So we get n factorial on the top, 12 factorial, 12 factorial on the top. On the bottom we get k factorial first, so 8 factorial. And then times n minus k, so that's 12 minus 8 factorial. So if I simplify this, this is 12 factorial over 8 factorial times 4 factorial. Then if I work this out with a calculator, we get 495. And that's our answer.